Continuing on a theme of routing, by now you've learned about the basics of routing, distance vector and link state algorithms, and how routing works in the internet, the structure of the internet, autonomous systems, the hierarchy of those autonomous systems, exterior routing protocols, interior routing protocols. So in this video, I'm going to tell you about the specific exterior routing protocol that all autonomous systems must use when connecting to their neighbors. That's BGP, or the Border Gateway Protocol, currently in version 4. Okay, let's start with the basics of BGP 4. BGP is not a link state or a distance vector routing protocol. Instead, it uses what's called a path vector. And the way this works is that the BGP routers at the boundary of each autonomous system will advertise a complete path, and that path is a list of ASs that you pass through in order to reach a particular destination prefix. This is also called the AS path, and that's the path vector. So an example of a path advertisement might look like this. It says the network prefix 171.64/16 can be reached via the path going through these three ASs, 1, 5, and 13. So that might be an example of an advertisement that BGP might advertise to one of its neighbors. The consequence of sending out a path is that paths with loops are very easily detected locally. You just look for repetition of an AS, and then you can simply remove those or just completely ignore those advertisements. And that makes it very easy to find and eliminate loops. But perhaps the most important feature of BGP is that local policies that are private and secret to a particular autonomous system can pick the preferred path among those that are advertised to it. So if a number of neighboring autonomous systems advertise different paths to reach the same prefix, then the local policy can pick whichever one it chooses, whichever one it wants. It's not accountable to anyone else when it's picking that. Finally, when a link or a router fails, the path is withdrawn, just like an advertisement comes with, just like the one above. A withdrawal would look very similar, in which it would say this particular prefix can no longer be reached via this path. So BGP4 starts with a relationship between customers and providers. Let's take a look at this. So let's start with drawing a particular AS. This would be the provider AS, the one that's the one sitting above in the hierarchy, and then the customer AS sitting below. The relationship between them is, although traffic can flow to or from the customer through the provider in either direction and may go off through multiple exit points, because of this specific relationship between them, and that relationship is one of provider to customer. It has specific implications, and one of them is that the customer will always pay the provider to carry its packets. So if we're thinking of how money flows, money is flowing up in this direction here. The customer is paying the provider in order to carry its packets. So this hierarchy of customers to providers continues. So if we have multiple ASs, so let's draw some ASs here and some down here. These could be the access ASs that we saw before. Then this relationship between them of provider towards customer could go like this. And what that tells us is that as before, the money is actually flowing in the other direction for settlement charges between them, and IP traffic can go in the following way. So IP traffic could flow from a customer up to its provider, down through its customer, and down through its customer down here. Similarly, something from here, traffic from here could flow through this way. If there was another relationship, for example, this particular this particular one access AS down here had relationships with providers above it in 2 places. Traffic is allowed to flow through any of these paths, so it could flow down this way or down this way. In general, they will not flow through an intermediate at the same level, and we'll see an example of that a little bit later. So the reason for telling you about this customer-provider hierarchy is we're going to see it show up a little bit later in the policies that BGP uses. And basically the peering relationship is as follows. So looking at this example here where we have, just as before, we have 3 ASs here, here, and here, which are the providers, and then 3 down here that are the customers of those. And the key here is telling us what the provider-customer relationship, and that these ones up here are peers of each other. So in general, a peer cannot be a transit for its other peers. In other words, this particular path that's shown here, the black dotted line, is not allowed because it's going through this peer. That's because typically the relationship here between 2 peers is settlement free. There's no dollars flowing across here. So peers do not provide transit between peers. Now let's take a look at BGP messages, and then we'll look at the policies that BGP implements. So there are basically 4 types of BGP message. There's an open message to establish a BGP session. There's a keep alive in order to provide a handshake at regular intervals. That's just basically an occasional message just to be able to check that the BGP session is still alive between 2 routers that are connected to each other. And there's a notification to shut down a peering session. So these 3 here, open, keep alive, and notification, are basically the ones that keep the session alive. The ones that actually announce and then withdraw routes are the update messages, and these are the most important ones. They announce new routes or they withdraw ones that were previously announced, and these are we saw an example of that earlier with the advertisement of the particular path for a prefix. An announcement basically consists of the prefix and then the path attributes. So it'll be the path of ASs and then attributes associated with it. And we'll see an example of that now. So the path attributes are the next hop information, where you go in order to be able to use this. In other words, who it is that's advertising this, this particular path to us. The particular AS path, so that's the sequence of ASs that you would go through. And then various other things, the local preference and the multi-exit discriminator, and there are various other parameters that are passed as well that tell us information that would allow us to pick the particular path when we receive multiple advertisements from different peers. So these are used to select amongst multiple options for paths, because we may hear from multiple peers on how to reach a particular destination prefix. And basically, when we have a choice, the sequence goes something like this. So we start with the highest local preference. This is the highest local preference. We'll see an example of that in a moment. It's a local preference that tells us how we enforce relationships. We might prefer customer routes over peer routes, and we'll see an example of that in a moment. If the local preference, which is essentially our local policy, if that doesn't tell us which particular path to pick when we have some choice, the next one is we'll simply pick the shortest autonomous system path. In other words, the shortest path to a destination. And then there are various other parameters that we might pick that are all to do with helping us do good traffic engineering. What this means is that we will tend to send traffic over lightly loaded paths and will cause less congestion in the network. But the ones that we are most interested in are the highest local preference and the shortest AS path. If all of these fail to distinguish or identify a particular path that we should choose, then we simply go with the lowest router ID. In other words, that's the lowest router ID of one of our neighbors, and that's essentially throwing up our hands and a means of breaking ties if there's no other way to pick between advertised routes. Let's take a look at how the autonomous system path, the AS path attribute, might work. So we'll look at an example of how we might pick the shortest path. So let's say that we are sitting over here at this particular autonomous system here, and we're hearing about a prefix that originated down here. Here's the prefix 135.207.0.0/16, and it originated from here. And so it will initially be advertised up here, and then it'll be advertised up here. And when it gets advertised here, it will say, you can reach this particular prefix, 135.207.0.0/16. You can reach it via AS7018 followed by 6341. And then that will flow around here, and then they've added one AS to the path, then it'll get advertised here. So by the time it comes down here, we will find out that the prefix 135.207/16 can be reached through 1129, 1755, and so on until we get to 7018. And likewise, there'll be an advertisement that will come around this path that will say, hey, I can get you to 135.207/16 through the sequence 7018, 3549. So it's over a much shorter path. So in this particular case, if I haven't got a higher local preference, then the router will say, this is the shorter path, and so I will pick as my favorite to send packets this way in order to reach this particular prefix. And so it will install that decision locally in its routers that says, when I see a packet with this prefix, then I'm going to send it out this direction, and that's my choice. There can be many, many choices. So let's look at an example here. So in this particular network, Frank's Internet Barn is trying to decide which route it should pick in order to reach this prefix 13.13/16, which is down here in AS1. The nature of the relationship here is that Frank is connected directly to a provider, AS4. It's connected to a peer, AS3, and it's connected to a customer, AS2, which in turn is connected to another customer down here. So we could have a number of different local preferences, and it might say I'm going to give a local preference of let's say 100 to my peer to customer, my provider to customer relationship. In other words, I'm going to give preference of 100 to routes that are advertised by my customers to me. And maybe I just say I'll give a local preference of 80 to ones that are received from my provider and 90 to ones that are received from my peer. What that basically says is, if I hear a route that arrives from my customer, I'm going to take that very seriously because that's a paying relationship, and I would prefer to send it to my customer rather than sending it over to a provider where I'm going to have to pay. So I'm going to give preference from if they're coming up through the from the customer. My second favorite choice is from a peer, because I don't pay there either, because it's presumably settlement free. But where I actually have to pay for the traffic is to the provider. So if I hear a route that's advertised down here, I'm not likely to pick that unless that's my only choice. So basically I'm saying, in terms of my choice, customer advertised routes are better than peer advertised routes, are better than provider advertised routes. And this is a pretty common for, it's not baked into BGP. You can just set the preference values to do this. You could also set the preference values to be the opposite, although that would be pretty unlikely. So when these advertisements are going to arrive for this particular AS, they're going to come up through here to Frank, they're going to come up through here to Frank, and they're going to come this way to Frank. Frank is going to pick the one that goes down through the customer. So when he sends traffic, he's going to send traffic down this way to AS1 because that's his favorite path, because that's the one with the lowest local preference. So local preference is the one that I use first. And if that doesn't tell me my choice, then I'll pick the shortest AS path, and then I'll walk down that list that was on the previous slide. So in summary, all autonomous systems in the internet must connect using BGP4. That's the exterior protocol that they must use to talk to their peers or to their neighbors, the routers at their neighboring autonomous system. BGP4 is a path vector algorithm. That means a list of the autonomous systems is sent along with every advertised prefix. And this allows loops to be detected very easily and for a router to examine that path and choose whether it wants to use it or not, depending on its policies. BGP4 has a rich and complex interface to let autonomous systems choose a local private policy based on all sorts of things. You could spend a whole quarter learning about nothing else than how BGP works and what the consequences are. There have been many, many papers written on the consequences of these policies. So each AS decides a local policy for traffic engineering, security, and any other private preferences that it might have, so that it can choose amongst advertised paths coming from different neighboring autonomous systems. That's the end of this video about BGP.